Welcome back. It's time for Wise Guys Wednesday.
UofI physics professor Paul Kwiat is showing us the relationship between glass of water and a fingerprint scanner. Take a look.
Hey everyone, nice to see you. Today we're actually in the middle of a series. We've been talking about piezoelectrics, which allow you to move things very small distances, and actually next week I'll maybe make the connection with how we can use that to be able to see atoms, individual atoms. But we need one more sort of interesting piece of physics, and that's in this glass of water. So this is going to be a bit of an interesting demo in that it's actually going to be easier for you to do at home than it is for me to show on the camera, but I'll still try to show it a little bit. Okay, so this is just a clear glass filled with water, and I'm just going to tilt my camera over here. You can see that if I bring my finger behind, you stop seeing my finger, okay? When it's under the surface of the water, you can't see it anymore. And that's because the surface of the back of the glass is effectively acting like a really good mirror. It's showing what's on the bottom. So I can convince you of that maybe by putting something underneath the glass. Let me just do that quick. Yeah, okay, and so now what you're seeing in the side is what's actually underneath the glass because the light is being reflected off the side of the glass. Okay, so that's called total internal reflection, but that's not really the main thing I want to show. It's a variation of that. So this is a thing that's a little bit hard to see. So I'm just going to bring my finger behind, and again, it's a little tricky to see, but if you look right under the bright light there, you can see as I'm pressing my finger, you can see a little spot. And if you were to look inside the glass, you'd be able to actually see my fingerprint. Unfortunately, the camera doesn't pick that up very well, so you just see it getting a little bit darker. But if you try this, you will definitely be able to see your fingerprint on the inside of the glass, or rather on the outside of the glass. So let's just try and explain what's going on with that. Let me just share my screen quick. Okay, so of course we all know that when you have light and it's normally traveling at the speed of light, and that can be different depending on what it's going through. So in air or in vacuum, it's more or less as fast as it can go, which we represent by the letter C, the speed of light in vacuum. But if it goes through a different material, it might be going slower than that, and we can characterize how slow it's going by the index of refraction. That's just the speed that it would go in vacuum divided by the speed it goes in the material. So n is always going to be, will never be less than 1. Could be bigger than 1. And if light goes, for example, from air into water, where it's going faster in the air and slower in the water, then it will bend or refract when it does that. And the slower it's going in this other material, the more that it will bend. So for example, if we go into diamond, it bends a lot. Okay, so let's start out now in the material where it's going very slowly and let it go into something where it's going less slowly. And if I tilt the beam, okay, I see that it's bending, and I get to this point, one point where all of the light suddenly is reflected. So a little bit before then, some of the light was refracted and transmitted, but now absolutely everything is reflected, and it just stays like it's a perfect mirror. So that's called total internal reflection. We could look at the same thing just with a demo. This was taken in my lab a little while ago. So I have a laser at the bottom. It's going through this semicircular prism. So this is the material where it's going slow. This is the material where it's going fast. And you see that right about now, we're about to have, oof, everything is now being reflected. So this is the total internal reflection condition. Okay, so what does that have to do with our fingerprint? So here again is, for example, a prism. And in a prism, I have total internal reflection here where the light is coming in and it's all bouncing off this interface. It turns out that a little bit of the light is sort of hanging out on the other side of this interface. It's not sticking out very far, maybe only 100 nanometers or so, so you know, 1,000th the size of a hair, a human hair. But if we can bring something close to that surface, for example, the ridges in my fingertip, in my fingerprint, that will do is that will frustrate the total internal reflection. So instead of having everything being reflected, wherever there are ridges in my fingerprint, the light will no longer be reflected. Some of it then instead will just be absorbed in my fingertip. And if in fact I put a sensor there at the bottom, I can then see where there was total internal reflection and where it was frustrated. And from that, I can get my fingerprint. And in fact, this is how some fingerprint scanners work on, for example, some laptops and such. Hopefully that was fun, and you can try this on your own. And maybe next week we'll make a connection between that and one of the coolest things in quantum mechanics called tunneling. Okay, hope to see you guys soon. Have a great week. Bye-bye.